Good morning, students. In the last lecture, we discussed the basic properties of determinant and we are doing some problems given in exercise 1. So I will continue with those problems. And question number 6, you have to prove that the this determinant value is equal to 2 into a plus b plus c whole cube. Now, see, just do some elementary transformation to bring the elements of first column in the form of a plus b plus c. We can do it very easily by this transformation. If we change the values of c1 with c1 plus c2 plus c3, that means first add c2 plus c3 and then C2 and C3 and then add with the corresponding terms of C1. Then we'll get the first column as 2 into A plus B plus C. The second column C plus B plus C plus 2A plus B. That means 2 into A plus B plus C, and third column also we are getting 2 into A plus B plus C. So in the first column, this 2 into A plus B plus C term is common, so take it outside and we will have this determinant. And now just change the second row and third row. If we change R2 into R2 minus R1 and R3 as R3 minus R1, then we'll get 2 zeros in the first column and it will make the determinant very simple. So after this transformation, we'll have this determinant 1 0 0. If we change R2 into R2 minus R1, that means here first row will remain same because there is no transformation in R1. So write the first row as 1AB. So 1AB. The second row we are transforming second row into second row minus the corresponding elements of first row, that is R2 minus R1. So 1 minus 1, 0. B plus C plus 2A minus A, that is B plus C plus A. B minus B, that is 0. So R2 is complete. Now R3, we are changing R3 into R3 minus R1. So 1 minus 1, 0. A minus A, 0. C plus A plus 2B minus B, that is C plus A plus B. Now, since we have 2 zeros in the first column, so just expand this determinant along the first column, or you can do along R3 also, because in R3 also we have 2 zeros. So it is up to you. After expanding, we are expanding, that means just along first column, that is 1 into, just ignore this particular row and particular column and cross multiply the remaining terms. So B plus C plus A into C plus A plus B minus 0 into 0, that is 0. So we are having A plus B plus C whole square. So whole square and 2 into A plus B plus C. So after multiplying this, we are getting 2 into A plus B plus C whole cube. So it is proved. Similarly, in question number 9, you have to show this determinant is equal to x plus 2a into x minus a whole square. First write this determinant. Now see how you can bring most of the terms equal so that you can take those terms common. And you have to prove here x minus a and x plus 2a. So try to bring these terms in your determinant. So if we just change the first row R1 as R1 minus R2 and second row, that is R2 as R2 minus R3, then what we'll get R1 is changed into R1 minus R2, that is x minus a minus x, a minus a, that is 0. First row is complete. Second row is getting changed into R2 minus R3. So R2 minus R3, a minus a, 0, x minus a, then a minus x. There is no change in R3, so write the terms as it is. So write AAX. Now we can write these terms like this also, taking minus common. So we can write here, you have to prove x minus a, so write those terms of a minus x in the form of x minus a by taking minus common. Now from R1 and R2 you can see there are common terms, that is x minus a. You can take x minus a common from R1 because in R1 two terms are x minus a and third term is 0. If it is not 0, then we cannot take common x minus a, but since the third term is 0 and the first and second term is same, so you can take x minus a common from R1, and similarly you can take x minus a common from R2 also. Okay, so after taking common R1 and R2 from x minus a from R1 and R2, we will have x minus a whole square. One from x minus a from R1 and another from R2. So it will be whole square. So remaining term 1 minus 1 0, 0 1 minus 1 and AAX. You cannot take a common from the third row because there is a and it is x. So write R3 as it is. In the next transformation we can do this because your attempt will be bring maximum term 0. So if we change C1 into C1 plus C2, if we add these two terms, then what would happen? 1 minus 1 0, 0 plus 1 1, a plus a 2a. Okay, and then minus 1 1a, 0 minus 1 x, right? C2 and C3 as it is. Now since in the first row we are having two zeros, so expand this determinant along R1 and we will have this value. If we expand this along R1, that is negative of negative 1, that is positive 1, and then ignore this particular row, particular column, and find the remaining terms, determinant value of the remaining terms. So 1 into x, that is x, minus of minus 1 into 2a, that is plus of 2a. So it will be negative, negative, positive, so x plus 2a. So x minus a whole square into x plus 2a. Now it is proved. Clear? And the next question number 11. The remaining question you try yourself. I'm doing question number 11 for you. You have to show this determinant value is equal to this. Now write the determinant. Now see, you have to bring the terms alpha minus beta, beta minus gamma, gamma minus alpha. Okay, so just transform C2 into C2 minus C1 and C3 as C3 minus C1. I am doing the transformation along in columns. You can do it by row also. You can change R2 as R2 minus R1 and R3 as R3 minus R1 also. Because I am doing, but I am doing here along column. So change C2 as C2 minus C1 and C3 as C3 minus C1. Then what will happen? There is no change in the first column, so write the terms as it is. So 1 alpha square alpha cube, so 1 alpha square alpha cube. In C2, C2 minus C1, that is C2 minus C1, 1 minus 1, 0, beta square minus alpha square, and then beta cube minus alpha cube. Done. Now third column, the elements of third column, the corresponding elements of first column. So 1 minus 1, 0, alpha square, gamma square minus alpha square, and then gamma cube minus alpha cube. Next, when you will expand this along the first row, because there are two zeros in the first row, so after expanding along the first row, we'll have the determinant value of the remaining submatrix, that is beta square minus alpha square, beta cube minus alpha cube, and gamma square minus alpha square, gamma cube minus alpha cube. So we are left with this determinant value after expanding along R1. Now, by this term, we can see very easily that if we write the formula of beta square minus alpha square, that is a square minus b square formula, a plus b into a minus b, that is beta plus alpha into beta minus alpha, right? This gamma plus alpha into gamma minus alpha. And then beta cube minus alpha cube can be written as in the formula of a cube minus b cube, that is a minus b, that is beta minus alpha, into a square plus ab plus b square, that is beta square plus alpha beta plus alpha square. And similarly, the form of gamma cube minus alpha cube can be written as gamma minus alpha into gamma square plus alpha gamma plus alpha square. We are writing this formula because after writing this, we will have the common terms in the first column also and in the second column also. So take beta minus alpha common from the first column and gamma minus alpha from the second column. So write these terms, common terms. Now you are left with the terms beta plus alpha, gamma plus alpha, and then this term beta square plus alpha square, and gamma square plus alpha gamma plus alpha square. Now in the next transformation, what we can do, just apply C1 into C1 minus C2. That means we are changing the first column into first column with the negative sign with the terms of the second column. That is, if we write beta plus alpha minus of gamma minus alpha, then we will, the alpha and alpha will get cancelled out. So we will left with only beta minus gamma, because we have already these terms alpha minus beta and beta minus gamma, but gamma minus alpha you have to bring, no? So for this, just write the terms of C1 as C1 minus C2. Then it will be beta minus gamma and beta square plus alpha square minus this term. So alpha square will get cancelled, and we will left with the term beta square minus gamma square plus alpha common beta minus gamma. And C2 will remain unchanged because there is no transformation in C2, only C1 we are changing. So write the terms as it is. This. Now you can see that there is common term in beta minus gamma in the first column, because here beta minus gamma, here if you write beta square minus gamma square in the form of beta plus gamma, beta minus gamma, then beta minus gamma you can take common. So beta minus gamma is common in this C1, so take it outside. So you will remain with the terms 1 gamma plus alpha, and then here if you take beta minus gamma common, you will have beta plus gamma plus alpha. So write this term. Now you can find the determinant value of this matrix. So cross multiply. So 1 into gamma square plus alpha square minus gamma plus alpha into beta plus gamma plus alpha. So after multiplying and then subtracting these terms, we'll have this term minus of alpha gamma minus of alpha beta minus of gamma beta. And this term can be written in this form. Clear? Alpha minus, take uh, um, this is negative sign, negative of beta minus alpha, gamma minus alpha, beta minus gamma can be written as negative of alpha minus beta, beta minus gamma, gamma minus alpha. And then here also you can take negative sign common, so negative, negative, positive, so you will have this term. Now it is proved. Now you can see how we can do those transformation to prove our result. Similarly, in this question number 14, we have to prove that this determinant value is equal to 4a square b square c square. So what we can do, just observe that in the first column, second column, third column, which term is common? The first column, a is common in all the terms, a square plus ab. So you can take a common from first column, b is common in the second column, c is common in the third column. So take a, b, c common from c1, c2, c3. So write a, b, c. You are left with the terms a plus b, and b. We are taking b common, so left with the term c plus c, b, and b plus c. And in the third column, after taking c common, you are left with the term a plus c, a, and c. Clear? Now apply this transformation. A, you are changing the first row, that is R1, as R1 minus R2 minus R3. Then what will happen? A minus A plus A minus A plus B, that is A minus B, and then again minus B. So you will have this term minus 2B. Second, C minus B minus B minus C. So you will have minus 2B. A plus C minus A minus C. So you will have 0. We are transforming only first row. So there is change in the first row. Second row, third row will remain same. Since now we are applying the this operation, that is C1 is changed into C1 minus C3. C1 is changed into C1 minus C3. That is minus 2B minus 0. That is minus 2B. B minus, sorry, after applying this, we are having this determinant. Now we are applying this operation. C1 is C1 minus C3. So minus 2B minus 0 minus 2B. A plus B minus A. So only B. B minus C. Okay. and C2 into C2 minus C3, so minus 2b is minus 0, as minus 2b, b minus a, and then b plus c minus a, that is b. After applying this, we are having this determinant. Now apply C2 as C2 minus C1. C2 as C2 minus C1. So minus 2b, first there is no operation in first column, so write the terms of first column as it is. Now C2 is getting changed into C2 minus C1. So minus 2b of minus 2b, that is plus 2b, it will be 0. B minus a minus b, so it will be only minus a. B minus b plus c, so it will be only c. There is no change in C3, so write 0 AC, 0 AC. Now you can see that there are two zeros in the first row, so expand the first, expand this determinant along R1, that is first row, and we'll have this determinant value ABC, and then minus 2B into, ignore this particular row and particular column, so we have minus AC and minus of again AC. So it will be minus of 2AC and then minus of 2B, multiply this and we will have 4A square, B square, C square. Is it fine? Now do the rest of the problems by yourself. Try it and please inform me whether you can do it or not. Now come to the last topic of your first unit. This will be the last lecture of your first unit, and it is about the application of determinants in solving a system of linear equation. That means now we will solve a system of linear equation by using determinant. In the previous exercise, we solved the system of linear equation by matrix method. That means by finding the inverse of a matrix, and then if we multiply the inverse of matrix with the constant term in the right hand side of the equation, then we'll have the values of the unknowns, that is x, y, z, if it is an equation of 3 variables. Now we'll solve a system of linear equation by Cramer's rule. This rule is given by the mathematician Cramer, so it is named after that German mathematician. It is a very short method to solve any system of linear equation. Matrix method is quite lengthy, but Cramer's rule, by using Cramer's rule, you can solve a system of linear equation of any number of variables very easily. Now let us see how you can do that. We can solve a system of simultaneous linear equations by Cramer's rule, and the method is given by, if we are taking first the example of two linear equation. If we have two equations with two variables, two linear equation, it will be in the form of linear, and suppose it is in the form of a1x plus b1y equal to c1 and a2x plus b2y equal to c2. So the formula to find the variable x and y is given by x equal to dx by d and y is equal to dy by d. These are the notation. D in the subscript we can write x, you can write 1 also, and here d in the subscript we can write y, or we can write d2 also. But we are writing dx and dy, where d is the coefficient matrix. That means d is the determinant of the coefficient matrix, that is D will be the determinant value of the coefficient of x and y. The coefficient of x is a1, a2, so write D as a1, a2. The coefficient of y is b1, b2, so write the second column b1, b2. So this is the determinant D. And what is the value of dx? Dx will be equal to, or d1, in some books it is written d1, so it is up to you. You can write dx or you can write d1. So dx is equal to, after changing the coefficient of x and the constant in the right hand side, that is c1, c2. We are replacing the coefficient value as the constant in the right hand side, that is c1, c2. And the second column, that is the coefficient of y will remain unchanged, that it will remain same, and denote it as dx. And dy will be the coefficient of y will get changed with the constant in the right hand side, and the first column, that is coefficient of x, will remain same, that is a1, a2 will remain same. You are changing the coefficient of y, that is b1, b2, as c1, c2. So this is the formula. That means first find determinant value if it is non-zero, because we are dividing the value of dx by d, so d should be non-zero. First find the value of d. If it is non-zero, then we can apply the Cramer's rule. So find the value of d and then find the value of dx. So in finding the value of dx, you have to just change the values of the coefficient of x in terms of the constant terms given in the given equation. That means here it is c1, c2. Similarly, find the value of dy, and we will get this determinant value after changing the coefficient of y as the constant terms in the right hand side, that is c1, c2. Now here you can see that D is the determinant of the coefficient matrices. The determinant dx is obtained by replacing the first column in D by the column on the right hand side of the given equation that I have already told you. And the determinant dy is obtained by replacing the second column in D by the rightmost column in the given system of equation. Rightmost column means the constant terms in the right hand side of this equation, that is right hand side. Okay, now let us take an example. Suppose this equation is given. Solve this equation by Cramer's rule. 2x minus 5 equal to 17, 3x plus 5y equal to 16. So first we have to find the value of d. The value of d, that means we have to write the coefficient of x and y. The coefficient of x and y, coefficient of x is 2 and 3, so in the first column 2, 3. Second column, coefficient of y, that is -1 and 5, so -1 and 5. Find its value, that it is, the value is 13, so it is non-zero. We can use the Cramer's rule. In the next step, you have to find the value of dx and then dy. Dx, that means you have to change the coefficient value of x as the terms in the right hand side, right hand side of the equality sign, that is 17, 6. So change 2, 3 into 17 and 6, and C2 will remain same. Find its value, 17 into 5, with negative sign, 6 into minus 1, so it is 91. Similarly, to find the value of dy, first column will be same as the coefficient matrix, that means D. So 2, 3, first column there is no change. In the second column, that is, we are finding the value of dy, that means we are changing the coefficients of y with the constant terms in the right hand side. That is 17 minus 1 and 5, minus 1 and 5 will get changed into 17 and 6. So the value of dy is minus 39. So use the Cramer's formula. It is given that x is equal to dx by d. So the value of dx is 91 and d was 13. So it is 7. And y is dy by d, that is minus 39 by 13. So it is minus 3. So x equal to 7, y equal to minus 3 is the value of the unknowns. So you are similarly, if we consider the system of three linear equations, that is, if you have three variables x, y, z, and this is given in this standard form of linear equation, that is a1x, b1y, c1z equal to d1, a2x, b2y plus c2z equal to d2, a3x, b3y, c3z equal to d3, then by Cramer's formula, we can write x is equal to dx by d, y is equal to dy by d, and z is equal to dz by d, where d is the determinant of the coefficient matrix, that is the coefficient of the variables x, y, z. In the variables of x is the coefficient of x is a1, a2, a3. So write d as a1, a2, a3. Coefficient of y is b1, b2, b3. So b1, b2, b3. Coefficient of z is c1, c2, c3. So write c1, c2, c3. So this is d. Similarly, to find the value of dx, that means you have to replace the value coefficient of x into d1, d2, d3, the constant term in the right hand side. So first column will change into d1, d2, d3, and the second, third column will remain same. To write dy, you have to change the column of the coefficient of y, that is b1, b2, b3 will get changed into d1, d2, d3, and c1 and c3 will remain same. Similarly, to find the value of dz, first and second column will remain same. The coefficient of z, that is third column, c2, c3, c1, c2, c3 will change into d1, d2, d3. Okay, and then find the variables x, y, z by using this Cramer's formula. It is very easy method. So I will give you just one example, and rest of the question given in your exercise 2, you can do that questions, you can practice those questions by using Cramer's rule also. So it is given that this is the system of linear equation. You have to find the solution by using Cramer's rule. So write first the coefficient matrix in the form of determinant, that is D is equal to 1, 1, 1. So 1, 1, 1, 1, 2, 4, 1, 2, 4, 1, 3, 9, 1, 3, 9. If it is given in your question that there is no term, suppose in y, in the third equation, suppose you are having only x plus 9z is equal to c, is equal to 6. Then in that case, you have to write, when you will write the second column, so then write 1, 2 and 0. If there is no term in y or in x or in z, then you have to write the coefficient of that variable 0. Okay, so it will be it is a square matrix. It is a matrix of 3 variables. It is given that 3 equations are given, so it will be a matrix of 3 cross 3 square matrix. It will be. So find the value of D. It is coming out 2, which is non-zero. Now you proceed. Now find dx. To find dx, replace this first column of the coefficient of x into 3, 4, 6. So write 1, 1, 1 as 3, 4, 6. Second, third column, there will be no change. Then find the value of the determinant. We'll get dx. Similarly, find dy. That means you are changing the coefficient of y column into the constant terms. 3, 4, 6. First column, third column will remain same. Find the value. Similarly, to find dz, first, second column will same. Change the value of third column into the constant terms in the right hand side, and you will have this value. Dz is 0. So we apply Cramer's rule, and that is x is equal to dx by d. So find dx is 4, d was 2, so it will be 2. Y is dy by d, so 2 by 2, that is 1. Z is dz by d, dz was 0, so 0 by 2, that is 0. So 2, 1, 0 is the solution of the given system of linear equation. So in this way, you can solve the system of equation very easily. So this is a very short method. If it is not mentioned in your questions that what method you have to use, you can you can use Cramer's rule, because it is more easy than the matrix method. Matrix method is quite lengthy, but it is up to you that what method you will choose if it is not mentioned. Okay, so I should stop here. Thank you.